So I'd like to start with acknowledging co-authors, my boss, Teddy Mankova, Kyle Martins, who's the DNR fish biologist, and we work closely with Ashley Steele and Alex Foster from Forest Service PNW. So the data that I'm going to be talking about today is just a small part of a much larger monitoring project that was initiated on the OESF in 2012. It's called Status and Trends Monitoring of Riparian and Aquatic Habitat. And in one sentence, it's basically looking at the long-term influence of DNR riparian management practices on in-stream and riparian habitat conditions. And so listed here are just a few of the different things that this monitoring project is monitoring. In case some of you are having deja vu, I did talk about this last year, but last year I talked about mostly stuff relating to vegetation, like the riparian forest, shading, in-stream wood, in-stream habitat. And I talked a little bit about summer stream temperatures. And in case you missed it, summer stream temperatures on DNR land in the OESF are looking pretty good. The vast majority of the streams are below any sort of regulatory thresholds. So today I'm just going to be talking about a subsection of this data, which is winter stream temperatures. Okay, so first of all, why are we interested in winter stream temperatures? Most people that monitor stream temperature look at summer, particularly summer maximum temperatures that could be harmful to fish and other organisms in the stream. But those same animals that are in the stream in the summer are also there in the winter, and they're also affected by the winter stream temperatures. For example, many species of fish are there, including the salmon, and things like egg emergence, development of young fish are influenced by temperature during the winter, as well as other vertebrate species and invertebrates that are prey in these streams. So objectives today is, first of all, I want to look at some landform influences. These are major landscape features that could affect winter stream temperatures in small fish-bearing streams. And I also want to review what happened in 2015. A lot of you probably remember that 2015 was an exceptionally warm winter, record temperatures in the mountains and low snowpack. And some people say that year is potentially representative of future climate conditions. So we want to see how 2015 was exceptional. Okay, so the monitoring design here, we selected 50 type 3 watersheds throughout the OESF, representing a range of size and elevation. And a type 3 watershed is defined as the drainage around a type 3 stream. And DNR's definition for type 3 stream is it's basically the smallest fish-bearing stream. And so you'll notice we have a couple of watersheds that were over here in Olympic National Park, and those are just to see what was happening in completely unmanaged conditions. So within each of these watersheds, we have a sample reach installed near the outlet of the watershed. And it's about a 100-meter sample reach, and that's where we monitored stream temperature. And to give you a quick overview of what these watersheds are like, average size is about 500 acres, but there's a big range from 37 up to almost 2,000 acres. Elevation is about 250 to 2,800 feet. Stream width, about 6 to 32 feet, and there's a pretty good range in gradient too. So we monitored temperature starting in late 2012 using these little waterproof temperature loggers, and we monitored at a 60-minute interval in those 54 different watersheds. We used a couple of different installation methods to secure the data logger in the stream. The challenge here is to keep the logger submerged in the stream during these low flow periods, and then at the same time you have to keep the logger from getting washed downstream during these super high flow periods when you have big rocks and boulders just moving. So luckily we have some pretty good field crews that can handle that kind of thing. So in recent years, this phrase thermal regime has been discussed, and this is basically looking beyond just like mean temperature and maximum temperature, which historically are what people used. But if you're interested in the effect of water temperature on the organisms that live in the water, you have to look further than just mean and max. You have to look at some different facets of the thermal regime. as it's called. And so for this project, we developed these different metrics to sort of describe what the stream temperature is in winter. I'm just going to go over these really briefly. So one of these is the mean temperature on the 15 coldest days, when the water is at its coldest. I'll call this, the extreme days in the winter. Then the 90 coldest days, mean stream temperature on those days is just a big, a broader descriptor of what's happening in winter. Then we define cold days as less than 43 Fahrenheit. So we look at the frequency of those cold days, how many consecutive cold days you get, the annual range in temperature in these streams, and the daily range in temperature in the winter. Timing, this is particularly important for species because a lot of species are accumulating degree days to determine where they are in their life cycle. So how long it takes to accumulate 1,000 degree days. And then we looked at the air-water relationship, and what that is just basically if you draw this regression line between air temperature and water temperature, it's just looking at how responsive the stream temperature is to the air temperature that day. And so if you have a steep line, it means your water temperature is going to change rapidly in response to air temperature. If you have a flatter line, water temperature is more stable regardless of what air temperature is doing. So I'm going to talk about 3 variables that we looked at today, that each of these variables we used to sort of try to explain changes in those metrics on the last slide. So the metrics, those 8 metrics on the last slide, what I'm going to focus on is Bankfull width, so basically just stream width. Bankfull width is measured at the more or less the annual high flow mark. Then elevation, which is self-explanatory, and then solar exposure is the third that I want to talk about. And that's basically a slightly fancier version of aspect. So what we did was use ArcGIS to create this model of solar exposure during winter. And so it took into account all sorts of things like slope, aspect, shading from nearby ridges and other topography. So you can see here, this is a river valley, and you can see the southern aspect is getting a lot more exposure to direct solar radiation. So those are the 3 variables that I'm going to talk about here. First of all, I want to show this slide just to indicate how complicated it is in streams in terms of figuring out what is heating and cooling the streams. I'm not going to talk about all these different things, but I just want to say that the importance of the different heat fluxes changes frequently throughout the year. It changes from day to night, it changes depending on weather. There's big differences from summer to winter. Like in summer, by far the major factor determining how warm a stream is direct solar radiation. I mean, that outweighs everything else on this chart. In winter though, you don't get that nearly as much direct solar radiation, and so all these fluxes are a lot more similar. They're smaller and they're similar in magnitude. The couple I'm going to be focusing on today are just heating and cooling at the air-water at the surface of the stream, the interface, and then the effect of groundwater and runoff on stream temperature. So because during winter especially, air does influence stream temperature, I just wanted to show this graph. And this is just an average across the study, just over a water year. The water year is just the year beginning October 1st, going through September 30th. So I've just plotted the water is this blue line, water temperature averaged across all the basins. And then air temperature is the red line. But what I want to focus on is the difference between air and water temperature, because that can tell you whether the air is cooling the stream or whether it's warming it. So what we see here is they're pretty similar in fall, and then you get into winter, and air temperature is colder than the water temperature. So this line here is below the 0 line. This green line at the bottom is below 0. And so that means that basically the air is cooling the stream, or the stream is losing its heat to the air. And then that shifts over in late spring, and the air becomes warmer than the water, and so the air starts to warm the water. But what we're focusing on today is winter. So that's basically when the air has that cooling effect. So I tried to squish 4 years of data into one slide, and I just want to show you just a big overview here of what winter stream temperature looks like in this area. And so the black line you see here on these graphs is just the average stream temperature across all of our streams. And 2 things I want to point out. One is that if you take a simple definition of winter is like December, January, February, it doesn't really apply so much here because we have this really long period where it's variable and temperatures stay pretty consistently cool for like 5 months. So it's not just like a 3-month winter. And the other thing is there's this huge variation during winter depending on weather patterns. You know, and if you compare that to what's happening in summertime, you know, things are not really changing that much in response to weather in summer. But in winter, we got these huge ups and downs here. Okay, so the first of those three landscape factors that affect stream temperature that I want to talk about is Bankfull width. And this slide is just to show you sort of the range and size of these streams that we're monitoring. This is one of the smallest ones. It's about 6 feet in Bankfull width that you would measure from here to across to here. This is a pretty average stream in terms of size. And this is one of the larger ones, which is about 30 feet in Bankfull width. So that's the range we're looking at. So to describe what Bankfull width, the influence of that on stream temperature, here I'm just listing the 8 different metrics I showed earlier, those extreme days, those, the larger 90 winter day period. And then, so here, for each 1 meter increase in Bankfull width, this is the change you would expect in those temperature metrics. So basically, if you're comparing a 4 meter wide stream and a 5 meter wide stream, you would expect it to be that much colder on the extreme cold days. I won't go through all of these, but I just want to say, big picture wise, all of these are indicating that for the larger streams during winter, they're colder than the smaller streams, which was not exactly what I expected. I was used to seeing, you know, used to thinking in terms of streams and rivers warming as you go downstream. So I wanted to take a look at why this was. So here I pulled out the smallest, the 5 smallest streams and the 5 largest streams in this monitoring project, and then just plotted them over the course of the winter, and also looked at the difference. And what I'm most interested in here is that difference between the smallest and the largest streams. So this line here at the bottom, when it goes above 0, when this green line goes above the dotted line, that means that the smaller streams are warmer. So what I was interested here is when are the smaller streams warmer? Well, it's interesting that when the overall temperature is lowest, when it gets down below about 5 or 6 degrees C, that's when we see the smaller streams become warmer. This isn't happening in the fall or the spring or the summer so much as in the winter. So you get that smaller stream warming effect in the winter. So to try to figure out why that was happening, here's a graph that shows the same thing, just zoomed in on a shorter time scale. So again, this line here, this line at the bottom, when it goes up, that means the smaller streams become warmer than the larger streams. And then the blue bars are daily precip measured right here in Forks. And so what we saw, and this was throughout the whole winter, is when you have precip, when you have these rain events, especially big storms, the smaller streams warm up. They warm up sooner than the larger streams. That blue line, it means the smaller streams are warming sooner, and they also warm up more than the larger streams. So basically what we're seeing here is that when you have this precip, most of it is runoff or groundwater. A lot of it enters the soil, then it flows down into the stream. And so when it's flowing down towards the stream, it's taking on whatever temperature the ground is. And when you have air temperature that's pretty close to freezing sometimes, the ground is actually warmer than the air. So the ground is warming that precip water. Then it enters the stream and has a warming effect on the stream. And then what this is showing, comparing the smallest and largest streams, is showing that those smaller streams are warmed more. They're more responsive to that warming than the larger streams. And we won't spend too long on this because it's kind of hard on the eyes, but this is just adding, we're also monitoring stream discharge. So we have stream flow here, that's the dotted line. And the blue line that's bouncing all over the place is average stream temperature across all the streams. So what this is showing is when you get these blue bars are the precip again, when you get a big precip event, you get this huge warming effect along with that huge increase in stream flow. So that pretty much explains why we're seeing these huge jumps in stream temperature during wintertime. So the second factor I want to talk about is elevation. This one should be a little bit more straightforward. I mean, most people know that air cools off when you get higher in elevation. To show you the range in elevation we're talking about, our lowest basin here is about 250 feet, the median elevation for that basin. And then at the higher range here, we get into 2,000 plus feet elevation. So when we look at those same metrics of stream temperature, we see that, again, these things that describe the general coldness of winter are affected, as you would expect, by elevation. You go up in elevation, things get colder. A couple that surprised me a little bit was those extreme days. The 15 coldest days of winter are not affected by elevation. So regardless of elevation, it gets just as cold on those coldest days of the year. And another thing is the variation. The annual variation and the daily variation are not influenced by elevation. So another one of these graphs, I want to show here pulled out the 5 lowest elevation streams and the 5 highest elevation streams, and again looked at the difference. I wanted to see when we're seeing that elevation effect. So if we're starting off here in the fall, as you would expect, lower elevation streams are warmer than higher elevation. And the same thing you see in the spring, especially in the late spring, lower is warmer. But then interestingly, like here, when the temperatures are coldest overall, when you start to approach freezing, temperatures are the same regardless of elevation. I wish I had a really cool explanation for this. I think rain on snow is probably a factor here. We don't have good rain on snow data across all these different watersheds though, so I can't say too much about that. But it's still a pattern that maybe will be looked at in more detail at some point. So the third factor is solar exposure. And again, looking at these 8 different metrics, what was interesting to me is solar exposure affected the 4 that were not affected by elevation. So the effect of elevation on stream temperature in winter and the effect of solar exposure is different. So, and you wouldn't know that unless you looked at all these different aspects of winter temperature. But here we see the coldest days are colder with more solar exposure. You get more variation within day, and also summer-winter variation, you get more. And finally, this air-water relationship is affected by how drainage is exposed to direct solar radiation. So I want to illustrate that with a couple of graphs. These are 2 basins. This one is high solar exposure. It's like a south-facing watershed. And this one is low solar exposure. It's probably one of the north-facing watersheds. Each dot here represents 1 day. So what we're looking at is the relationship between winter air temperature and winter water temperature. So in the case of the one where you have south-facing, high solar exposure, water temperature increases on average 0.43 degrees for every degree increase in air temperature. And over here you have only a 0.24 degree effect. So this was a little interesting to me. I would expect this in the summertime. I'd expect to see exposure to solar radiation influencing stream temperature, but it was interesting to see this also occurring in the wintertime. Something I didn't expect. So I want to shift gears for the last couple of minutes and talk about what happened in winter 2015. It's that winter when we had exceptionally warm temperatures. This is December and January temperatures. There was records set at all higher elevations, very low snowpack, near record temperatures at the lower elevations too. And this is not just like a one-time thing. Several years ago, a study came out monitoring coastal Pacific Northwest streams since the 70s and showed a long-term warming trend. But where that warming trend really came out was for winter temperatures, even more than summer or fall temperatures. So winter and early spring temperatures are on this long-term warming trend. So that's part of the reason we wanted to look at 2015. So just to compare month by month, this red line here is what happened in 2015, and the black is all of our other years. And so you can see during the winter months, we had close to 2 degrees C difference. So Fahrenheit, that's about 3 to 4 degree average difference. But then just to show what was really happening when we look at a day-to-day time scale, this bold black line is 2015, and all these gray lines in the background are all the other years. So you can see the pattern is pretty similar. It bounces around a lot, just like the other years, but everything is just shifted warmer. Then if we look again at those metrics, they all show, comparing 2015 to the other years, they all show it is warmer. And particularly I want to point out the degree day accumulation. So if you're a salmon egg waiting to emerge, or salmon waiting to emerge from egg, and it takes 1,000 degree days before emergence, you're looking at a 22-day difference in 2015 versus the other years. I'm not a fish biologist, but that could probably have some implications on the life cycle. Okay, so finally, what we're seeing so far in this data set is that landscape features are influencing winter stream temperatures. For example, we saw that happened with stream size and storm events. Interestingly, elevation and solar exposure have different effects on temperature in winter. Some biologists might need to consider looking in the future. For example, when we looked at 2015, I saw The day-to-day patterns and landform influences were similar to the other years. Things were just warmer. And so finally, understanding of this winter thermal regime will probably become increasingly important if we see streams in this part of the country continue to warm during wintertime. So finally, I'd just like to thank the field staff that we've had that worked hard on this project. If you have any questions, I'll either try to answer them or refer them to a co-author. So, thank you.